You break the magnets apart, you still have a north and a south. The field lines go from north to south. It's a closed space. If you have an electron all by itself, its field lines go infinitely far away. They get weaker and weaker by the inverse square law, but magnetic fields stay within themselves. Notice the solenoid on the right or a bar magnet. They're very much the same. If you put an electric current through that wire, through the solenoid, you'll create a magnet that looks much like a bar magnet. If you put enough current through, you'll get the same magnetic strength as you do through the bar magnet. If you put something inside the solenoid, you can increase the magnetic field by making the field lines denser. What we do in modern electronics, though, is use toroids, not solenoids, because we can keep more of the magnetic field in place and we get less interaction with other magnetic fields. Unfortunately, the quality factor is much, much better for a solenoidal coil than it is for a toroidal coil. So that means you've taken something that was very, very highly tuned and now you've spread it out more. So you need to put more filtering in later on, even though you've gotten rid of the interaction. So it's a little trade-off. In receivers, there's always trade-offs. Mr. Faraday was the guy that came up with the magnetostatic idea. Mr. Oersted was giving a physics lecture one day in about 1820 when he came along and he set up he had his compass sitting right next to his wire, and he threw the knife switch, sent a current through there, and all of a sudden he saw the meter. He saw his compass move. And like, that's odd. Right in the middle of a lecture, no less. So he opened up the knife switch, and the needle went back to where it's supposed to go. He did this a few times, and he's looking at that, and his students are wondering what's going on, and they can't see the compass going. So he kind of found this serendipitously. Mr. Faraday did this, and he was the one, Mr. Faraday, Michael Faraday, came up with inductance, and he did a lot of work with transformers. Because if you have one solenoid right next to another solenoid, or if you have a toroid that's wound with one wire and then another wire, you've made a transformer, and you can take high voltage and low current, and you can take it and change it into low voltage and high current. Or you can make an isolating transformer and put in the same voltage on one side and the same current, get the same on the other side, but you basically electrically isolated these two circuits. As long as you send in AC on one side, get AC out on the other, you'll get the same thing. But you've made sure to protect yourself from shorting yourself off to ground, and it's a good thing. I think I've covered it. Next we come along to electromotive, where things are getting interesting because there's motion involved. The del cross E is, let's get the right hand rule. If I put a current through a wire, yay, the thumb is the direction of current. In our modern sense, electrons flow, but Mr. Franklin said no, positive. That's why we're always pointing in the wrong direction. But the magnetic field lines go like my fingers. They're at right angles and they're circular around the current, around the wire carrying the current. Now, what happens is, if I turn on my electric field and then turn it off again, there's a time constant. All of a sudden, the field builds up and I have a nice magnetic field. Then I shut off the power, but the magnetic field stays there and it gradually decays in an exponential form. Just like capacitance, it falls off exponentially.
Starting out rather rapidly.
Oh yeah, it's really steep, but it holds on for a while. And if you've ever held on to the ends of an inductor, when it goes off, you feel the inductive kick. That's why you need to put a diode in the other direction to get rid of that, or else you'll start burning things up, because there's a lot of voltage going in the opposite direction. But because if you put an AC voltage through, an AC current through an inductor, it will start coming out the other side, even though there's nothing connecting it. It's like magic, but it's opposite each time it flips. Oops, I should get on the right page. This is called Faraday's law for induction. And the interesting thing is, if we do this properly, we make our coil, we send it through a magnetic field, we get a nice AC waveform out there. If you put in the right commutator, you'll get out a DC waveform. It'll have ripple in it, but you'll have a DC waveform. But this is how you can make a generator for AC. The next stage is, how do we do this without having magnets? That's the real trick, and that's where Mr. Ampere and Mr. Maxwell came along and developed this equation. Mr. Ampere came along and had del cross B, which is magnetism, and the partial E with respect to T, which means as the electric field changes with time, you create a magnetic field at right angles to it. Same right-hand rule. So as the current changes, the strength of the field in that circular electric field, the magnetic field, will change in time with it. Mr. Maxwell came up with these little fudge factors of mu 0, epsilon 0, and then J is called the displacement current. And this is one of these things in theory where it's kind of like radiation resistance. It doesn't really exist, but it really helps the math. It's kind of a fudge factor just to make everything balance on both sides of the equation. That's all it did.
Well, they threw away 16 of the other things, right? So they had to come up with something.
Pretty much. But this, if done properly, is how you have an alternator. Remember back here, we have this magnet which generates the magnetic field, and then we use, say, water to spin our coil through this magnetic field. Well, what happens if we go back a few stages, back to here, and we send our electricity through a solenoid, and then instead of this magnet, we have the solenoid making a magnetic field from an electric field, and then we spin our wires through that. We now have an alternator. That's why your car won't start unless you have electricity, or your motorcycle won't start. If you pull start your lawnmower, there's magnets in there, so you have a generator. But if it's an alternator system, you need to have electrical power to create the magnetic field, to create the electric field. You're just kind of stuck. No battery, it doesn't work. But it's kind of neat. I was going to make some toys, and I'm still going to try to do it. I was going to generate power for you by shaking something through a tube and a coil, a magnet through a coil, and then I was going to put a coil around a penlight battery, shake the same thing, and show you, here's how I can light an LED with a magnet, here's how I can light an LED with a penlight cell on a coil. It should work.
And then you were explaining how they shake flashlights work, almost of it.
Yeah, and then you put in a full wave rectifier to make DC out of it. It should work just fine to light an LED.
I think
although
we
you might have to kill the lights. I'm not sure how bright it's going to be. Now we come to, this is closer to antennas than we were before. Notes to page 2. How well can you see this, JD? Fine, okay, I wasn't sure if I got that big enough. The three basic things in AC, much like in a DC circuit where we have Ohm's law of volts and amperes and ohms of resistance, well, in an AC circuit, we have E equals IZ, where E equals volts. I'm more of a V person than U person, but E equals volts, I equals current. Z is impedance. Z is the AC equivalent of resistance. Resistance is essentially friction against the motion of electrons. In DC, it's in one direction. In AC, it's in both directions. And this is what we try to get rid of when we are making an antenna. We want to get rid of the reactance. We want to get rid of our impedance. We want to get rid of the AC portion of the impedance. Correct that. It's resistance is present in all conductors to some extent, most notably in resistors. When alternating current goes through a resistance, a voltage drop is produced that is in phase with the current. Remember that, in phase.